Welcome to this presentation on step response equivalent approximation. In this lecture, we will obtain from Laplace domain transfer functions step response equivalent approximation, same as zero order hold equivalent approximation. We will show some examples and a Scilab code. Consider the discrete time signals obtained with zero order hold. Suppose we want to discretize the analog transfer function GA of S, it is an S domain in Laplace transform. Let us obtain step response from it, call the step response as Ys of t, discretize this continuous signal to get Ys of NTS, Ts being the sampling time, takes the transform of these discrete time signals, you get Ys of Z capital Y, divide the result from the above by the Z transform of a step, namely Z over Z minus 1 to get G of Z. Okay, here is the formula. You take step response of the continuous time system, invert it, get the continuous time signal, discretize it and take Z transform of it and then multiply by the reciprocal of the Z transform of a step signal. This is known as the step response equivalent. This looks like the zero order hold equivalence approach that we studied earlier. This is step response because we are holding the signal constant. Here you can see that this looks like a step signal and so on. Here it looks like a negative step signal. So this is known as the step response approach. This also looks like the zero order hold equivalence approach. In fact, in an example given in the textbook, we show that the step response equivalence is the same as the zero order hold equivalence. Both approaches give rise to an identical discrete time transfer function G of Z. We will consider some examples. Let us calculate the step response equivalent of 1 over S. The step response of 1 over S is 1 over S squared. In time domain it is Laplace inverse of 1 over S squared, which is equal to t. Now sample it with a period of Ts, we get Ys of NTS as n of Ts. Let us take Z transform of this, you get Ys of Z, it becomes ZTS by Z minus 1 whole squared. We have seen this earlier from the Z transform of n. Z transform of n is Z over Z minus 1 whole squared and you have the Ts appearing here. Let us divide now by the Z transform of a unit step, which is Z over Z minus 1. We get the discrete time equivalent, which is Gz equals Ts over Z minus 1. Next, let us take the Z transform of n and n squared. Using this slide, we have already seen this. From here we got the Z transform of n. From here you can get the Z transform of n squared minus n. If you add the Z transform of n to this, you will get the Z transform of n squared here. This is something we have already seen. We will use this result from here, the Z transform of n squared. That is useful to calculate the step response equivalent of 1 over S squared. So you give a step input to this and you get 1 over S cube as the response, invert it, Laplace inverse of 1 over S cube is half t squared. Let us sample it with a period of Ts, you get this expression. Here we use the Z transform of n squared. Let us take the Z transform of this, using the result given in the previous slide, you get this expression. Now once again divide by z over z minus 1, we get this transfer function. So as in the previous slides, the z transform of the transfer function given in the title is obtained here. Now let us discretize a first order transfer function. Let us say that the transfer function is given by k over tau s plus 1. Find the step response, multiply by 1 over s, do a partial fraction expansion. From here you get ys of t, which is equal to k times the inverse of this is 1, and then the inverse of this is exponential minus t over tau. These are standard results that one knows from Laplace transform, and of course t is greater or equal to 0. Let us discretize it. T equals nts, replace this t with nts, and for n greater or equal to 0. Let us take z transform. In the place of 1 we have z over z minus 1. This looks like r to the power n, where r is given by exponential minus ts by tau, and the z transform is z over z minus r. As a result, we get this as the z transform of the second expression, and this can be simplified. It is easy to calculate this. Next we have to divide by the z transform of unit step. Let us divide by this, and this z over z minus 1 will go away, and you get this expression. In the next slide we will do sample calculation, and I want you to remember this expression, and in particular this exponent here, which is minus ts by tau, which is the sampling time divided by the time constant. You have to remember this. If you want, you can even write it down. So the transfer function is given by 10 over 5s plus 1. Let us sample it at ts equals 0.5, that is sampling period is 0.5. Of course it is assumed that consistent time units are used. Typically these could be seconds. In chemical engineering these could be minutes also, but if it is not stated, we generally take it as seconds. Let us sample it and find the 0 order hold equivalent transfer function. The Scilab code is given here. It is just 2 lines, and the Scilab output is given here, which can be written in this fashion, where this 10 is a steady state gain. And what about this 0.1? 0.1 turns out to be ts by tau. So you have ts by tau here, here also ts by tau in the exponent. So we conclude that this is in agreement with the formula in the previous slide. With this we have come to the end of this presentation. Thanks for joining. Goodbye.